this unit, we are going to discuss microwave spectroscopy, and we are going to cover the topics rotational spectra of diatomic molecules, rigid rotor, diatomic molecules, reduced mass, rotational constant, effect of isotopic substitution, non-rigid rotator, centrifugal distortion constant, intensity of spectral lines, polyatomic molecules, linear, symmetric, asymmetric top molecules, hyperfine structure, and the quadrupole moment of linear molecules, instrumentation techniques, block diagram, information derived from rotational spectra, star effect, and some problems. So in this class, we are going to discuss these topics: rotational spectra of diatomic molecules, rigid rotor, diatomic molecules, reduced mass, and rotational constant. The transition between two energy levels will be recorded in terms of spectra. We know about very well. If the transition between two rotational energy levels of any molecule which is having the property of rotation, then the radiation which is coming out will lie in the microwave region. Those spectra are called as microwave spectra or rotational spectra. Microwave spectroscopy gives information about the dipole moment and the moment of inertia of a gas phase molecule because the photon energies correspond to transitions between different rotational levels. So before going to start, let us have some introduction about microwave spectroscopy. Rotational energies of molecules are quantized. That is, they have definite energies only E equals NH nu. Here E is the energy in joules, H is Planck constant in joule second, nu is the rotational frequency in hertz, and N is an integer. The range of frequencies of rotational molecules is about 8 in 10 power 10 to 4 into 10 power 11 hertz, which corresponds to the wavelengths 0.75 millimeter to 3.75 millimeter. These wavelengths fall in the microwave region of the electromagnetic spectrum. Microwaves lie between radio waves and infrared waves in the electromagnetic spectrum. Microwave frequencies range between 300 MHz and 300 GHz. Wavelengths range from 1 meter up to 1 millimeter. Microwaves were first predicted by James Clerk Maxwell in the year 1864 by the use of equations. Later, during 1888, Henry Hertz proved the existence of microwaves by building a device that produced and detected microwave radiation. Spectroscopy is defined as the interaction between the matter and the electromagnetic radiation. It is one of the most powerful tools available for the study of atomic and molecular structure and is used in the analysis of a wide range of samples. The microwave spectroscopy deals with the pure rotational motion of the molecules. It is also known as rotational spectroscopy. The condition for observing resonance in that region is that molecules must possess permanent dipole moments. If molecules are not having dipole moments interaction, then these molecules are said to be microwave inactive. For example, hydrogen, chlorine, and so on. If molecules are having dipole moment, then their interaction will give rise to a spectrum. Such molecules are said to be microwave active. For example, hydrogen chloride, methyl chloride. The determination of those frequencies of the microwave spectrum that are selectively absorbed by certain materials, providing information about atomic, molecular, and crystalline structure. Due to rotation of charged molecule, induced electric field is produced, which will interact with the electric field component of external microwave radiation. Microwave spectroscopy is used as a tool for studying the structures of atoms and molecules. The large number of wavelengths emitted by these systems makes it possible to investigate their structures in detail. This includes the electron configurations of ground and various excited states. Theory of microwave spectroscopy. When transition occurs in rotational energy level, when the energy is absorbed and the peak appears in rotational spectra of that molecule. Thus, due to the interaction between light and matter, the energy can be absorbed or emitted, and the rotational energy level gives rise to a spectrum. In homonuclear molecules like N2 and O2, no change occurs in dipole moment during the rotation. So, the linear diatomic molecules are rotationally inactive for rotation about the bond axis. Thus, the homonuclear molecules, however, show rotational Raman spectra, which arises due to the polarizability of the molecules. Let us discuss about the dipole moment. So, charges are separated with some distance are called dipole. It is a product of magnitude, positive and negative charges. They are separated, and the distance between the bond length. Bond is nothing but internuclear distance. The molecule possesses rotational energy due to rotational motion. The rotation energy of a molecule is quantized. When the molecules undergo transition from one rotation energy level to another, it emits or absorbs electromagnetic radiation of suitable wavelength. On this way, the spectrum of a molecule is obtained, which is known as rotational spectrum. The condition for microwave spectroscopy. Molecule must possess permanent dipole moment. Molecule having a dipole moment rotate, it generates an electric field which interacts with the electric component of the microwave radiation. During the interaction, energy can be absorbed or emitted, and thus the rotation of molecules give rise to a spectrum. This is the main topic of this unit. Rigid rotor, which is nothing but diatomic molecules. We are going to discuss the reduced mass and rotational constant. Consider a diatomic molecule with different atoms of mass M1 and M2, whose distance from the center of mass are R1 and R2 respectively, and the system is balanced about its center of gravity. So this is as shown in the figure. So we have different masses M1 and M2. There are two atoms, and the distance between two atoms is nothing but R, and the center of mass is here somewhere. So we assume a rigid, not elastic bond between the two molecules is as shown in figure exactly 1.1. A rotating diatomic molecule with nuclei separated by a definite mean distance is treated as a rigid rotator, which we study in macroscopic level, and the distance between two masses is constant. That is, in a molecule, the bond length of two atoms is constant, but this will rotate with the angular motion. A diatomic molecule can rotate n over n above the center of mass, and the rotational energy is quantized. This energy is limited to certain definite values depending on the shape and size of the concerned molecule. Here, the n over n rotation means the molecule interchange. The molecule will interchange to this side and this side, about in the center of mass. And figure shows a rigid diatomic molecule treated as two molecules of masses M1 and M2 joined by the rigid rod of length. From the figure, see the figure. So here, this distance, the internuclear distance is nothing but your R. R1 is about the center of mass from the M1 mass, and the R2 is from the center of mass to the mass of the another atom M2. So it shows that R equals R1 plus R2, and R1 equals R minus R2, and R2 equals R minus R1, we know. According to the law of balance, M1 R1 equals M2 R2. So therefore, R1 equals M2 R2 divided by M1, as shown in equation 1.3. Similarly, we can get R2 from equation 1.2 as R2 equals M1 R1 divided by M2. The moment of inertia of the molecule over the center of gravity can be written as I equals M1 R1 square plus M2 R2 square. Putting the values of R1 and R2 in equation 1.5, we have I equals, this equation can be written as I equals M1 R1 multiplied by R1 plus M2 R2 multiplied by R2. We can substitute the expression for R1, which is given as M2 R2 divided by M1. And here we can substitute the expression for R2, which is given as M1 R1 by M2. And this M1 and this M1 get cancelled. And this M2 and this M2 will get cancelled. We have I equals M2 R1 R2 plus M1 R1 R2. Keeping the common terms out, so that will give us M1 plus M2 times R1 R2. Since from equation 1.2, 1.2 is given as M1 R1 equals M2 R2, which is the law of balance. So M1 R1 equals M2. Instead of R2, substitute R minus R1. So we'll have M2 R minus M2 R1. You bring minus M2 R1 from right hand to left hand side. We'll have M1 R1 plus M2 R1, which is equal to M2 R. So taking the common term R1 out. So M1 plus M2 R1 equals M2 R. So therefore R1 is expressed as M2 divided by M1 plus M2 times R. Similarly, one can get the expression for R2. R2 equals M1 divided by M1 plus M2 times R. Now, putting the values of R1 and R2 is equation 1.6. So this is equation 1.6. So I equals M1 plus M2 R1 R2. So I equals M1 plus M2 times, instead of R1 we can substitute M2R divided by M1 plus M2. Instead of R2 you can substitute M1R divided by M1 plus M2. And M1 plus M2, this M1 plus M2, with both will get cancelled. We have M1 multiplied by M2 and we have R multiplied by R will give us R squared divided by M1 plus M2. So this expression M1 plus M2 divided by M1 M2 divided by M1 plus M2 can be replaced with mu, which is the expression for reduced mass of the system. So here the two body system is now simplified as one body system about the center of mass. So this mu is called as reduced mass. To simplify the system further, so equation 1.9 becomes I equals mu mr squared. And equation 1.10 defines the moment of inertia in terms of atomic masses and bond length. This bond length is nothing but internuclear distance between two atoms. Thus, the diatomic molecule is equivalent to a single point mass at a fixed distance r from the axis of rotation. Such a system is called a rigid rotator. We know that the angular momentum L equals I omega. So the atoms, they are rotating about its axis, center of mass. So surely there must be an angular momentum. So L equals I omega. With the quantum number, it has to satisfy with the quantum number L equals root of j into j plus 1 h bar, as per Schrödinger equation. According to classical mechanics, the body with moment of inertia I can rotate with any angular velocity omega, and hence its energy can vary continuously. But for a system of molecular dimension, quantum restrictions can be applied. According to Schrödinger equation, only those energy levels are allowed for the rigid atomic rotor, for which I omega, which is equal to h divided by root 2 pi root of j into j plus 1. Here h is the Planck's constant and j is the rotational quantum number. And of course, they can replace by h bar, which is the reduced Planck's constant, which is given as h divided by 2 pi. So we know that half mv squared is nothing but ordinary kinetic energy. Now, since two atoms are rotating, so we have to go only with the rotational kinetic energy. So which is equal to half I omega squared. So here half mv squared, just to replace b equals r omega. So v squared equals r squared omega squared. So we can have 1 by 2 m r squared omega squared. Mr squared is nothing but your I. So 1 by 2 I omega squared. So the rotational kinetic energy is given as 1 by 2 I omega squared. Multiply and divide by I will give you 1 by 2 I squared omega squared divided by I. And we know that L equals I omega. So which is equal to h divided by 2 pi root of j into j plus 1. So instead of I omega, you can write this. I squared omega squared can be replaced by this. So we have Ej equals L square divided by 2y. Substituting the values of I omega in equation 1.111, we have the rotation energy, expression for rotational kinetic energy, which is equal to 1 by 2 h square divided by 4 pi squared I times J into J plus 1 joules. So this is the expression for rotation energy for diatomic molecules. And I can take one h to the left hand side, so that will give me nu. Nu equals E by h, which is equal to h divided by 8 pi squared I times J into J plus 1 hertz. And of course I can write this as nu equals C by lambda. I can write nu equals C by lambda, which is equal to h divided by 8 pi squared I times J into J plus 1. And I can bring this C to the right hand side, that will give me h divided by 8 pi squared IC times J into J plus 1. And 1 by lambda is nothing but nu bar, what we call this as a wave number. We are interested in differences between the energies, particularly in the corresponding frequency or wave number of the radiation emitted or observed as a consequence of changes between the energy levels. So that's why the spectra are usually discussed in terms of wave number in the rotational region. So this is in terms of centimeter power minus 1. Since for a molecule h bar is constant, we can write this equation as Ej equals J plus 1 h bar square divided by 2i, where J goes from 0, 1 to dot dot dot. So when J equals 0, you substitute J equals 0 here, E0 becomes 0. When J equal to 1, E1 becomes, you substitute J equal to 1 here, we will have 2 h bar square divided by 2y. J equals 2 gives us E2 equals 6 h bar square divided by 2y. And corresponding energy levels, which is nothing but the spectra, are given on the right hand side. For J equal to 0, E0 is given as the ground state. For the first excited state, that is the transition from the ground state to the first level, because it absorbs the energy from the external photon and it rises to the first level. So J equal to 1, it gives us E1. And similarly for the second step, and similarly for the third step, it gives us E2, E3. Transition between one level to another level takes place only by means of absorption spectra in the diatomic molecules, which is known as rotational spectra. And we are talking about here, it is absorption. It goes from one level to another level because it absorbs the energy from the external photon, and it has to obey certain rule, what we call the selection rule, which is nothing but del J plus or minus 1. So here absorption takes place one step up or one step down. Suppose if it is one step up, it absorbs from one level to another level. Suppose it comes from up to down, one step down, that means it has to emit some radiations. So at the time we will have del J equals minus 1. So plus 1 stands for absorption, minus 1 stands for emission. And the spectral lines which you are going to obtain in the spectra is as shown. This can be experimentally observed. And the first line says that J goes, that is the transition takes place from J to J plus 1. And this line goes from J plus 1 to J plus 2. The difference between these two will give us del nu. So nu equal to E by h. So Ej equals J into J plus 1 h bar square divided by 2y. We will calculate now absorption from J to J plus 1 level. And we know that Ej is given as J into J plus 1 h bar square divided by 2y. So nu J is nothing but, I can bring one, I can take this as E by h, which is nothing but nu. So which is equal to J into J plus 1 times h bar square divided by 2y h. Here I have divided on both sides by h. That will give me nu J. So we'll calculate now the frequency from this j to j plus 1. We substitute here. So we have j, instead of j, you'll have to go with j plus 1. So j plus 1 becomes j plus 2. So j plus 1 multiplied by j plus 2, h bar square divided by 2y minus, this is jth level. So j into j plus 1, h bar square divided by 2y. Just take the common term out. So j plus 1, taking the common term, that will give you j plus 1. And here it is j plus 2. Here it is minus j times h bar square. This j and minus j will get cancelled. We have 2 times j plus 1 divided by 2ih. This 2 and this 2 will get cancelled. So we have j plus 1 h bar square divided by ih. So for one h bar, I can write h divided by 2 pi, and this h will get cancelled. So we have new j to j plus 1 will give us j plus 1 h bar divided by 2 pi I. Now let us calculate now absorption from j plus 1 to j plus 2 level. So new j plus 1 to j plus 2 is given by this expression, that is j plus 2 multiplied by j plus 3 minus j plus 1 j plus 2 h bar square divided by 2ih. So taking the common term out, common term is nothing but j plus 2. The remaining term will be j plus 3 minus j minus 1. So j plus 2, j plus 3 minus j minus 1 h bar square divided by 2ih. So this j and minus j will get cancelled. 3 minus 1 will give us 2. And that 2 and the denominator 2 is that both will get cancelled. So we have j plus 2 h bar square divided by ih. And as usual, we just have for one h bar, we can write h divided by 2 pi. This h and this h will cancel. We have j plus 2 h bar times h bar divided by 2 pi I. Now, we are going to get, we should calculate now del nu, the difference between this level and this level. We have already calculated j to j plus 1 here. We have just now we have calculated j plus 1 to j plus 2. So this one. So this minus this will give me del nu. This minus this. See, del nu is nothing but nu j plus 1 to j plus 2 minus nu j to j plus 1. So h bar divided by 2 pi I, j plus 2 minus j minus 1. So 2 minus 1, this j and this j will get cancelled. So we have 2 minus 1 is nothing but 1. So del nu is nothing but h bar divided by 2 pi I. So this is experimentally observed value. And what is the use? So this is experimentally observed value. If I know this value, I can get the value of moment of inertia I. And of course, I know the expression for reduced mass is by m1 m2 divided by m1 plus m2. If I know the masses of two atoms in a diatomic molecule, I can get the value of bond length, which is nothing but the internuclear distance. So if we take the microwave spectra of molecules having permanent dipole moment, we can get the difference between two frequencies. If we know the moment of inertia, reduced mass, we can get the value of bond length. This is known as microwave spectroscopy or rotational spectroscopy. So the expression is given as for the rotational energy Ej equals h square divided by 8 pi squared I times j into j plus 1. In this expression, h is Planck's constant, I is the moment of inertia, the quantity j, which takes the integral values from 0 upwards, and this is called a rotational quantum number. The rotational spectrum can be recorded and studied. The separation between adjacent lines is 2b, which you are going to see now. From this value of 2b, the value of b is calculated, where b equals h divided by 8 pi squared IC. From the value of b, I can be calculated. From the value of I, R can be calculated. We'll see now how to calculate now b. In the rotational region, spectra are usually discussed in terms of wave numbers, as we have seen earlier. So, the wave number is given as Ej divided by hc, which is equal to h divided by 8 pi squared IC j times j into j plus 1, where c is the velocity of light. Equation 1.17 can be abbreviated as nu j bar, which is equal to bj j plus 1, where b is the rotational constant, which is given as h divided by 8 pi squared IC. The unit of b is nothing but centimeter power minus 1. Now, energy levels of a rigid dynamic rotor is obtained by this equation. So, wave number, which is equal to b times rotational constant times multiplied by j into j plus 1, where j equals 0, 1, 2, 3 goes on. So, you substitute j equals 0, this represents the first level, that is this level, ground state, ground level. And when you take it for higher levels, j equals 1, j equal to 2, j equal to 3, below corresponding values as 2b, 6b, 4b, and goes on. Here, look at the spacing, they are not uniform. Very important one. So, this is the allowed rotation energy of rigid diatomic molecules. The spacing between these two levels, they increase when you are increasing j values. Selection rules. A molecule has a rotational spectrum only if it has a permanent dipole moment. The selection rule goes with del j equals plus or minus 1. Plus 1 stands for absorption of photon and minus 1 stands for emission of photon. Transitions observed between two lines in absorption spectrum is given by, so between these two lines, when j equals 0 to j plus 1, we can get del nu j, which is equal to nu j equals 1 minus nu j equals 0, which is equal to 2b minus 0, which is nothing but 2b. The unit will be centimeter power minus 1. An absorption line will appear at 2b, centimeter power minus 1. And j equals 1 to j equals 2, again we will have del nu j, which is equal to nu j equals 2 minus nu j equals 1, which is equal to 6b minus 2b. We'll have to use this formula, 2b j plus 1, centimeter power minus 1. So we'll have 4b. So in general, the wave number, which is equal to 2b j plus 1, centimeter power minus 1. Look at here. Here it is the first one 2b, and here it is 4b, and the next line will be 6b. The difference, the spacing between two lines in the spectrum is nothing but 2b, where b is the rotation constant. By knowing the value of moment of inertia, I, we can calculate the rotational energy by Ej equals L squared by 2y, where L squared, which is equal to j into j plus 1, h squared divided by 4 pi squared. When you substitute the value of j, we will get a rotational energy Ej. The rotation energy for a rigid diatomic rotor is quantized, which is given as Ej equals j into j plus 1, h squared divided by 8 pi squared I. The unit of this one will be joules, where j equals 1, 2, 3. J is the rotational quantum number. Rotational energy is usually expressed in terms of, in the units of centimeter power minus 1. We know that E equals h nu and h is equal to c by lambda. 1 by lambda is nothing but v nu bar. So therefore, nu bar, which is equal to wave number, which is equal to E by hc. So the wave number, which is equal to rotational kinetic energy divided by hc, which is equal to h squared j into j plus 1 divided by 4 pi squared 2y multiplied by hc. So we will have h divided by 8 pi squared IC times j into j plus 1. It is in centimeter power minus 1. B is a rotational constant. Unit is given as centimeter power minus 1. So the wave number, which is equal to B times j into j plus 1, where B equals h divided by 8 pi squared IC, which is equal to h bar divided by 4 pi IC. The wave number gives the allowed energy levels of the rigid rotor, and B can be determined experimentally by spectroscopy. Applications of microwave spectroscopy. We can determine the moment of inertia of diatomic molecule. So B is recorded from the spectrum. We can get the moment of inertia using this formula. B is known from the spectrum. We can determine the bond length of any diatomic molecule. I equals m1 m2 divided by m1 plus m2 r square, which is equal to mu r square. So the bond length, internuclear distance of two atoms can be easily calculated. So R equals root of I by mu. Some limitations of microwave spectroscopy. Microwave spectra can be applied only for molecules having permanent dipole moment. The sample must be in a gaseous state.